Hello everyone, my name is Alexander Matsuoka, and this is my design review, the Magna. So here's the agenda that I'm going to be going over today. Why did I choose Magna as a name? I'm going to be going over the MIPS ISA. Then I'm going to show you my hardware block diagrams, the enhancements to the baseline, and then I'm going to also show you my SIMD vector unit and the future enhancements that I hope to add. So while I was trying to think of a name for my CPU processor, my MIPS, I thought, why not name it after one of my favorite things, Norse mythology? And it's not quite on the level of the god of thunder, Thor, but I thought, Magni, it's pretty close, son of Thor. He's mighty, brave, and great. It's one of my favorite stories from Norse mythology. So the memory. Memory is Harvard memory architecture, so basically it has separate signal pathways for instruction and data memory. This allows transfers to be performed simultaneously with different buses. Instruction and data memories use 32-bit addresses. It's byte addressable memory, and we use big N. So the data types that I used are 32-bit signed integers, 32-bit unsigned, and I have a vector unit, so it does 64-bit unsigned integers. The addressing modes for the thing is immediate. An immediate addressing mode is where the operand itself is part of the instruction. This mode is useful for initializing registers with address or data constants in programs. We also use register direct. Register direct is a direct addressing mode where the instruction contains the address of the operand. Direct addressing may also be referred to as absolute addressing. Register indirect addressing mode is where it specifies the register holding the address of the operand. This mode is used to access memory operands pointed to by base pointers that are stored in registers.
So do you really have instructions that use register indirect?
Mm-hmm.
Which ones?
I'll go over that.
Okay.
And then base index mode calculates the effective address, use base registers, and sign extent offset fields specified within the instruction. And that's maybe. Jump instructions. So I'm going to go over the instruction types. I have J-type instructions. They have an opcode specify the jump, so it's 26-bit, and then the first 6 most significant bits are the opcode for jumps. Register instructions. R-type instructions can contain up to 2 source operands right here, and then a destination register, and then there's also the shift and mount, and the function and opcode. The immediate instruction, so there is RS and RT, and an immediate 16-bit value that we use. And then for my enhancements, I did SIMD. So this is my vector register instruction. So basically, I have the E key at first, and then I have 2 operands for, it could be either registers or vectors. And there's also VD, which is the destination. And I also have a third register, could also be a register or a vector at C. And then for my jump flag instructions, which is also an enhancement, I have a 20-bit offset that will be added to the program counter if the flag is true. So here is my block diagram for the top level. Fairly simple. You have your control signals, and then you have your interrupts, and then the address and data buses. So if we go into the CPU, you have my data path, my integer data path. It's fairly just the normal baseline, simple. I didn't change it too much. The only thing really different is the V_DT, where I take in vector data for TMUX. And then there's the shift and mount for the ALU that goes into the ALU, because I don't have a barrel shifter. Now this is my SIMD data path. So basically, so this is my vector unit. So I have 3 registers. So I have the S, T, and C register that you can get from the vector register file. There's 32 64-bit vectors in the register file. You can get the data so I get the data from the GPR. Right there, it goes into the register file. That's how I can write. And from GPR, that's a control signal that I get from the MCU. The vector ALU basically houses all the operations that I need, which I will go over shortly. And then there's my Y reg, so that the result is stored into the Y register. And then since I don't have 64-bit data buses, I set it high or low, and then I have a Y select, so I decide whether I want to have the high bits or like the low bits.
So you're just breaking it into 232s.
Yes.
What is that signal from GPR? I mean, what does it control?
So that's from the MCU.
Right. What's it?
Whenever I have an enhancement vector called, and then I need to write to the vector register file.
So it's like a load signal?
Yeah.
Okay.
So these are the enhancements that I added to the baseline. I added rotate right, rotate left. I added all the jump flags and a couple SIMD instructions. So first off, rotate, basic rotate left, rotate right. Here's my logic that I used. I don't have a barrel shifter, so I just decided to go with shifting it left, 32 minus shift amount, and then I ORed it with the shift reg that I have that's specified by the IR, and then the shift amount. So that this is my Verilog implementation. This is basically in my ALU that I have. So this is the 2 rotates that I have. So it takes the Y low, it stores it into the Y low, it takes it from the T register, which is my shift reg, and then shift amount.
Is the carry flag going to be set
No.
on your rotates?
So these are the jump flags that I added. I added carry, 0, negative, and I think I just added those 3. So I added jump flag as a true enhancement. The MCU checks if the specified flag is true, and the offset is added to the PC if the flag is true. So if flag is true, PC gets PC plus, sign extended 25 to 6 IR. So here is my code from the instruction unit. So I added an if statement to my logic. So I added if jump flag, which is set in the MCU. And then PC in gets PC reg plus IR reg, so sign extended value. And then here's the MCU. So see, I set the jump flag to be true. And then in the PC signals, I say if C is 1, then I add the proper control signals. If it isn't, then I don't do it.
So that's in the instruction unit, that top.
This one is in the instruction.
You added that always block in the instruction unit.
Yes. And so here are the list of the SIMD instructions that I added. I added move vector, general purpose register, so that moves a vector into the general purpose register. It splits it into 2. And then I have move vector, vector purpose register, so it takes 2. Actually, no, I got that backwards. Move vector takes 2 registers and it puts it into a vector. And then move vector, vector purpose register takes vector and puts it into 2 registers. And then vector add unsigned saturated, vector multiply and add, multiply even integer. I'll go over all these in a few seconds. Merge low, merge high, compare, then I compare less than. So this is move vector general purpose register. So you take the RS and the RT that you specified, and then you concatenate them together and then you store it into the register file, the vector register file. So it's specified as VD. So
Do you have any RTL, or are you gonna get to that level, or you just have the general
I
idea?
just have the general.
Okay.
And then move vector, vector purpose register, it splits the 64-bit value into two 32 bits and stores them into RS and RT.
Do you recall how many steps that took?
This took two.
Just two states to do that?
Yeah. If I had a 64 data bus, I think I could do it in one. But it took
Yeah,
two.
right.
So this is the vector add unsigned saturated. So the purpose is to add 8 bytes to another 8 bytes in one instruction. So these are going to be two vectors, and then every byte I'm going to add, every 8 bytes I'm going to add, and then it's going to be stored into the destination register. And I think I have example. Okay, so here is what I have in my my vector ALU. So add unsigned. So basically, you can ignore the wrap right now because that's going to be a future enhancement. I'm trying to do signed, but that's just for future projects. But basically, I take the S and the T, and I add them together. I take 8 bits from the S and then 8 bits from T, and then I just add together and get the value, and I just store it into the 8 bits of Y. So multiply add. So this one, it takes 3 registers and 1 destination register. What you're going to do is you're going to have the 3 registers. So the first 2 are going to be multiplied. So their corresponding elements are going to be multiplied together. And then the 3rd register is going to be added to the result of those 2 registers. And that's going to be stored into the destination register. So that's happening right here. So I have, so the S low register, the 8 bits, the T low register, 8 bits are multiplied together. The result is added to C low, and then you store that into Y. So multiply odd and even immediate integers, not integers. So each even or odd element of a vector is multiplied to the corresponding element of the other vector. So when you multiply, you get a bigger value than this. So what you do is you multiply these 2 together, and then you store that into the corresponding elements of the destination register. Same with these 2 right here. And you ignore this one. If it was odd, then this would be this register, this 8-bit value. This would be this one, so on.
I think that one is odd, right?
This one's even.
So you consider
this
that
is
as
0, this
element
is 1,
0, okay, so
2.
you're going this way with your numbering. Okay.
So here's multiply odd integers, multiply even integers. So you can see how listed differently. So this one's going to be even integers. This one's odd integers, so it has 15 to 8. This one's 7 to 0. Compare if equal vectors. So compare each element of the 2 vectors, and if they are equal, then you store a 1 in the corresponding element. If it doesn't equal, then you store a 0. It's fairly simple. So simple check if the 8 bits are equal, not store 1, not store 0. 8 bits is 0. And then compare less than. Same thing as compare if equal. You compare the 2 elements, and then you store it into the destination register vector. So yeah, almost the same logic, just change the sign. So merge low, merge high. These ones I had a little bit of trouble, but managed to get it working in time. So the purpose is to merge the high or low elements of the source vectors into alternating elements of the destination vector. So what you do is basically you take the odd, or not the odd, you take the low of this vector and the low of this vector, and then it gets stored alternating in a fashion like that, so it makes a checkerboard pattern. Same with merge high over there. So get that value. It's fairly simple in a way. So it's trouble with it.
So why'd you have trouble there?
Turns out I put like a couple of the wrong numbers.
Oh, okay.
And I didn't catch it.
Subscripts.
Yeah. Okay. And so that's the end of the SIMD instructions I added. So for feature enhancements, I'd like to add a floating point data type, at least. Possibly pipelining. I don't know if I can do it. Again, I'm by myself, so it's like kind of a lot of work that I had to do. But definitely, I think I can add a 64-bit bus implementation because I think it would really help with the SIMD implementation. 'Cause,
What do you mean a 64-bit bus? External 64-bit bus?
in the top level, instead of having to do Y high and Y low, I would just like load 64-bit value. That way I don't have to take 2 clock cycles for some of my instructions.
So are you talking about writing to memory?
Yeah.
Or just transferring between? Yeah, I'm not sure what that means, 64-bit bus.
I want to do both writing to memory, 64-bit values, and I also want to externally transfer.
Okay, okay. Yeah.
Yeah, that's it.
For a one-person team, you did a great job, Alex.